Welcome, curious minds, to the deep dive. Today, we're going on an adventure into something absolutely fundamental to our world, yet it often operates completely behind the scenes. Materials. Think about it from the very first stone tools that launched human civilization to the tiny, intricate components inside the device you're listening on right now. Materials have really been the bedrock of human progress.
It's pretty mind-blowing, isn't it? How much human advancement right from the start has always been so deeply connected to how well we can make and manipulate materials. Just look at how we label historical eras. The Stone Age, the Bronze Age, the Iron Age.
Yeah.
We literally name them after the dominant materials of their time. It tells you, well, pretty much everything you need to know about their importance.
Exactly. And that's our mission today. We're going to crack open Chapter 1 of Callister and Rethwish's Materials, Science, and Engineering, an introduction. Our goal is to pull out the absolute most important nuggets of knowledge, the core concepts, and the game-changing definitions. We want to give you a clear, concise understanding of this field, like a supercharged shortcut to being well-informed without feeling overwhelmed, and we'll make sure you can picture everything we're talking about, even without visual. The book's title has Materials Science and Materials Engineering. Is there a meaningful distinction there, or are we just talking about two sides of the same coin?
That's a great question. And yeah, it's definitely two sides of the same, very important coin. Material science is really all about understanding why a material behaves the way it does. It's kind of the detective work, investigating the internal structures of materials and how they lead to specific properties.
Okay, the underlying reasons.
Exactly. Whereas materials engineering takes that fundamental understanding and uses it to design or, well, engineer a material structure to achieve a very specific set of properties for a particular application. So science is the why, and engineering is the how do we make it do what we want.
So discovery meets application. And I guess you often find people in the field skilled at both.
Oh, absolutely.
Yeah.
Most people working in materials are trained in both aspects. It makes total sense.
Now, a huge part of understanding this field revolves around structure and properties. Let's start with structure. When the book talks about a material's structure, what exactly are we picturing?
Right. The simplest way to think about structure is, well, it's the internal blueprint of what's inside a material. It's how all its components are arranged. And this exists at multiple levels of scale. It's not just one thing.
Multiple levels.
Yeah. We start incredibly small with subatomic structure and atomic structure.
Sure.
These refer to, the electrons within individual atoms and then how those atoms are organized, maybe into molecules, maybe into crystals.
Okay, the very fundamentals.
Exactly. But where things get really interesting for engineers are the slightly larger, yet still microscopic scales. We have nanostructure, which deals with aggregates of atoms forming particles so tiny they're less than about 100 nanometers.
Wow, that's small, like compared to a human hair.
Oh, way smaller. A human hair is maybe 80,000 nanometers thick, so we're talking really tiny. Then there's microstructure. These are structural elements you can actually see with a microscope, typically from 100 nanometers up to, say, a few millimeters.
So things like grain boundaries in metals.
Precisely. Things like that. And finally, macrostructure. These are the larger structural elements you can see with the naked eye. Anything from a few millimeters up to a meter, maybe even bigger.
Okay.
Understanding these different scales of structure is really key because changes at any level, even the nanoscale, can dramatically alter a material's behavior.
Fascinating. So if structure is the internal architecture, then property must be how that architecture actually behaves. Like when you poke it, prod it, or heat it up. Is that the right way to think about it?
You've absolutely got it. The core insight here is that a material's property is its inherent personality, you could say. It's how it always reacts to a specific stimulus, whether it's a tiny chip or a massive beam.
Regardless of shape or size.
Exactly. That independence is what makes properties so powerful for engineers. The chapter groups virtually all important properties into 6 main categories. Makes it easier to grasp.
Okay, what are they?
First, mechanical properties. This describes how a material deforms or maybe even breaks under an applied force. Think of its stiffness, its strength, or its resistance to snapping, its toughness.
Right, how strong it is.
Second, electrical properties. That's its response to an electric field. This includes its electrical conductivity, how well it lets current flow, or its dielectric constant, which is basically its ability to store electrical energy.
Like in a capacitor.
Exactly. Third, thermal properties, how it reacts to changes in temperature, things like thermal expansion, how much it grows when heated, or its heat capacity, how much energy it takes to warm it up. Fourth, magnetic properties. Describes a material's response to a magnetic field. Its magnetic susceptibility, for example, how easily it can be magnetized.
Got it. Like iron versus aluminum.
Precisely. Fifth, optical properties. This details how it interacts with light, its index of refraction, how much light bends going through it, or its reflectivity, how shiny it is.
Makes sense.
And sixth, deteriorative characteristics. This relates to a material's chemical reactivity, like its corrosion resistance, how well it stands up to rust or decay.
Okay, that's a comprehensive list. Now, this is where it gets really interesting, connecting all these ideas. The chapter introduces this crucial interrelationship, a kind of cycle among four key components: processing, structure, properties, and ultimate performance. It's often called the central paradigm, right?
Absolutely, the central paradigm. This is, well, it's essentially the roadmap for selecting and designing materials. It's had a huge influence. The idea is actually pretty simple when you break it down. The way we process a material, how we make it, shape it, heat treat it maybe, that profoundly influences its internal structure.
Okay, the making affects the inside.
Right. Then that structure, in turn, dictates all its inherent properties, its strength, its conductivity, its transparency, all those things we just listed.
Structure determines behavior.
Yes. And finally, those properties determine how well the material actually performs in a real-world application. It's a direct chain. Processing leads to structure, leads to properties, which leads to performance.
Processing,
Yeah.
structure, properties of performance. Got it. And the chapter gives a fantastic visual example using aluminum oxide discs that really drives this home. Can you describe that?
Oh yeah, it's a great one. Imagine three very thin, identical-sized discs made of aluminum oxide. You place them over a printed page. The first disc on the left, it's transparent. You can read the text clearly right through it.
Okay.
The middle one is translucent. You can sort of see through it, but the print looks blurry, indistinct.
Right.
And the one on the right is totally opaque. You can't see the print at all.
And the punchline is?
The punchline is, all three are made of the exact same chemical compound aluminum oxide, chemically identical.
Wow, so what's different?
The difference in how they transmit light comes down entirely to their internal structure. And that structure was created by how they were processed.
Ah, the paradigm in action.
Exactly. The transparent one is a single crystal, highly perfect, no internal boundaries to scatter light. The translucent one has lots of small interconnected crystals. Those boundaries between the crystals scatter some of the light, making it blurry. And the opaque one, it has many crystals plus tiny pores, like little air bubbles scattered throughout. Those scatter even more light, making it impossible to see through.
That's a brilliant illustration. Processing changes structure, structure changes properties, in this case light transmittance, and that changes performance whether you can read through it. So zooming out again, for someone listening, maybe an engineering student, why is internalizing this materials paradigm so fundamentally important? What's the biggest mistake you see people make when they don't quite grasp it?
Well, it's critical because, simply put, everything engineers design is made of materials. Everything. And if you don't understand this connection, you're essentially picking materials blind. It's guesswork.
Which is risky.
Very risky. When you're selecting a material, the book highlights three paramount criteria you have to consider. First, the in-service conditions. What demands will be placed on this material? High temperatures, extreme pressures. Does it need to be super strong or maybe super flexible?
What does the job require?
Exactly. And you often have to make trade-offs here. For instance, a material with incredibly high strength might be very brittle, prone to shattering. You can't always have everything.
Okay, trade-offs. What else?
Second, you must consider deterioration. How will the material hold up over time in its environment? Will it rust? Will UV light degrade it? Will it weaken at high temperatures?
Durability, essentially.
Right. And third, and this is often the decider, economics. What's the total cost? Not just the raw material, but the cost to shape it, finish it, the whole finished product. This almost always forces compromises. Maybe the best material is just too expensive.
Cost is king, often.
Often, yes. So missing any of these service conditions, deterioration economics means you'll likely pick the wrong material. And that can lead to failures, sometimes catastrophic ones.
And speaking of catastrophic consequences, the chapter includes a really powerful case study, the Liberty ship failures during World War II.
Yeah.
It's a sobering example of brittle fracture, isn't it?
It really is a stark reminder. During the war, the U.S. rapidly built thousands of these cargo ships, just churning them out. But many developed these alarming cracks in their decks and hulls, and shockingly, 3 of them catastrophically split right in half.
Split in half.
Yeah, one just a day after its launch in 1943. Imagine that. Investigations eventually revealed several critical factors all playing together.
What did they find?
Firstly, the steel they used exhibited something called a ductile to brittle transition at low temperatures.
Meaning?
Meaning it was normally tough and could bend ductile. But in the frigid waters of the North Atlantic, it became brittle. Like glass, it lost its toughness.
Okay, so the cold was a major factor.
Huge factor. Secondly, they found that square corners on hatches acted as stress concentration points. Basically, sharp corners where stress builds up, making it easy for cracks to start.
Like tearing paper from a sharp edge.
Exactly that idea. Third, the new welding techniques they used, while much faster for wartime production. Well, they allowed cracks, once started, to just run unimpeded for huge distances across the welded plates.
Unlike older methods.
Right. Traditional riveting usually stopped cracks at the edge of each plate. Welding created one continuous pass. And finally, just the sheer speed of production meant weld defects were often introduced by inexperienced operators. Little flaws that became big problems.
That's a perfect storm of material issues and design flaws.
It really was.
Yeah.
But crucially, these terrible failures led to massive improvements.
Like what?
Better quality steel with lower transition temperatures, rounded hatch corners to eliminate those stress risers, things called crack arresting devices built into the hull, and vastly improved welding practices and inspection.
So failure directly led to learning and innovation.
Absolutely. These failures hugely advanced our understanding of how cracks form and grow. It basically gave birth to the entire discipline of fracture mechanics. It's a powerful, if tragic, lesson in how deeply understanding material properties directly saves lives and drives innovation forward.
Okay, let's shift gears a bit and zoom out to the big categories of materials. The chapter groups solid materials into 3 primary classifications and then talks about composites and advanced materials. Where do we begin?
Right. We start with the big 3, which are classified based on their chemical makeup and atomic structure. First up, metals. These are primarily metallic elements. Think iron, aluminum, copper, gold, often with small amounts of non-metallic elements mixed in, like carbon and steel. Their atoms are typically arranged in a very orderly, crystalline pattern. And a key feature is they have lots of non-localized electrons.
Electrons that aren't tied to one atom.
Exactly. They're free to roam throughout the metal. Because of this structure and these electrons, metals generally have relatively high densities, they're quite stiff and strong, yet they're typically ductile.
Meaning they can bend or stretch a lot before breaking?
Right. They deform plastically, and they're generally resistant to fracture, quite tough. Those free-moving electrons also make them excellent conductors of both electricity and heat.
Makes sense.
They're also opaque, you can't see through them, and usually lustrous, meaning shiny when polished. And some, like iron, cobalt, and nickel, are magnetic.
Okay, so that's metals. What's next?
Next, ceramics. These are generally compounds formed between metallic and non-metallic elements. Often, they are oxides, nitrides, or carbides. Common examples include aluminum oxide, like our disc example, silicon dioxide, which is basically sand or quartz, traditional clay-based materials like porcelain and bricks, cement, and glass.
So a pretty diverse group. How do their properties compare to metals?
Property-wise, they are generally stiff and strong, often comparable to metals in strength and stiffness, and they're typically very hard. But historically, their big drawback is that they're quite brittle. They tend to fracture suddenly with little warning.
Less forgiving than metals.
Much less forgiving traditionally. Though, like I said, new engineering is constantly working to improve their toughness. Electrically and thermally, they're typically excellent insulators, very poor conductors compared to metals.
Opposite of metals in that sense.
Exactly. Optically, as we saw with the aluminum oxide example, they run the gamut. They can be transparent, translucent, or opaque. Think teacups, bricks, window glass.
Okay. Metals, ceramics. What's the third pillar?
The third is polymers. These are your familiar plastics and rubbers. They're often organic compounds, based primarily on carbon and hydrogen, sometimes with other non-metallic elements like oxygen, nitrogen, chlorine. Their defining feature is their structure. Very large, long, chain-like molecules. Think of spaghetti strands, but on a molecular level.
Big molecules. How does that affect properties?
Well, if you compare them to metals or ceramics, polymers generally have low densities. They're lightweight. They aren't usually as stiff or strong. Though, interestingly, on a per-mass basis like strength-to-weight ratio, some polymers can be surprisingly competitive with metals.
Ah, good point. Lightweight strength.
Right. They are often extremely ductile and pliable, very flexible. This makes them easy to mold into complex shapes at relatively low temperatures. Chemically, they tend to be quite inert, meaning they don't react easily with many substances. And like ceramics, they're typically excellent electrical insulators and are non-magnetic.
Any major downsides?
A big one is their temperature sensitivity. They tend to soften or even decompose at relatively modest temperatures, much lower than metals or most ceramics can handle.
Okay, so plastic tableware, bike helmets, milk jugs, those are all polymers.
Exactly.
To bring these classifications together, let's look at something simple. The carbonated beverage container. We see them made of all three types, right?
Yes, it's a perfect real-world example of material selection trade-offs. What do you need in a beverage container? It needs to hold the pressure, be a good barrier to CO2 escaping, be non-toxic, unreactive with the drink, strong enough to survive being dropped, relatively inexpensive, and maybe transparent.
Lots of requirements.
Definitely. So let's compare. Aluminum cans, that's the metal. They're strong but can bend. Very good CO2 barrier. Easily recycled, cool down fast. But they're opaque.
Can't see inside.
Right. Glass bottles, that's a ceramic. Impervious to CO2, chemically inert, inexpensive, recyclable, transparent. But heavy and fractures easily if you drop it.
We've all experienced that.
Haven't we just? Then plastic bottles, usually PT plastic, a polymer. They're strong for their weight, can be transparent, very lightweight, inexpensive. But they're less impervious to CO2 than glass or aluminum.
Ah, so that's why soda goes flat faster in a big plastic bottle.
That's exactly why. It's not just your imagination. The CO2 molecules can actually slowly diffuse through the polymer walls over time. It's the material properties at work.
Mind blown. Okay, so we have metals, ceramics, polymers. Then the chapter introduces composites. These are kind of like hybrid materials.
Precisely. You can think of them as engineered mixtures. A composite deliberately combines two or more individual materials, and they can be drawn from any of the categories we just discussed: metals, ceramics, polymers. The goal is always to achieve a combination of properties that you simply can't get from any single constituent material on its own.
Trying to get the best characteristics of each component.
Exactly. You're trying to synergize. We see natural composites all around us, like wood, cellulose fibers, and a lignin matrix, or bone. But most we talk about in engineering are synthetic, human-made.
Like what?
A classic example is fiberglass. You take small, strong, stiff, but brittle glass fibers, a ceramic, and embed them in a flexible, low-density polymer matrix. The result? A material that's relatively stiff, strong, reasonably flexible, and has a low density. Much better overall performance for certain applications than either glass or polymer alone.
Used in boats, car bodies, things like that.
You got it. Even more advanced is carbon fiber reinforced polymer, or CFRP. Here, you use incredibly strong and stiff carbon fibers embedded in a polymer matrix. These are even stiffer and stronger than fiberglass, though also more expensive.
Where do we find CFRP?
High-performance applications. Aircraft components, aerospace structures, high-end sporting equipment like racing bikes or tennis rackets. The fuselage of the Boeing 787 Dreamliner, for example, is largely made of CFRP composites.
Very cool. Now, the chapter also introduces a really useful visual tool for comparing materials. Materials property charts, sometimes called Ashby charts. Can you describe those?
Yeah, Ashby charts are incredibly powerful. Imagine a graph, but instead of linear scales, both the x and y axes are logarithmic. You plot one material property against another, for example, maybe Young's modulus, which is a measure of stiffness, versus density.
Okay, stiffness versus weight, essentially.
Right. Now, what's cool is that when you plot data points for specific material types, like all the common metals or all the engineering polymers, they don't just scatter randomly. They tend to cluster together in distinct regions on the chart. These regions are often enclosed within boundary lines, creating what look like bubbles or envelopes.
So there's a metals bubble, a ceramics bubble, a polymers bubble.
Exactly. And maybe bubbles for foams, elastomers, rubbery polymers, natural materials like wood, and composites too. These charts give you a simple yet really comprehensive visual way to compare the property ranges and correlations across a vast number of different material types all at once.
How do engineers use them?
They're invaluable for assessing trade-offs. Say you need a material that is both very light and very stiff. You look at the stiffness versus density chart, find the region that meets both criteria, and see which material bubbles overlap with that region. It helps you narrow down the choices very quickly.
A visual shortcut for material selection.
A very powerful one, yes.
Okay, moving beyond these basic classifications and tools, let's talk about advanced materials. These sound like the cutting-edge stuff driving high-tech applications today. What defines them?
That's a good way to put it. Advanced materials are generally materials used in high-technology applications. They can be traditional materials, like metals, ceramics, or polymers, whose properties have been enhanced somehow. Or they might be entirely newly developed, high-performance substances. They are typically more expensive than the conventional materials we've discussed.
What are some key examples?
Well, first up, a category that basically enabled our entire digital world: semiconductors. Their electrical properties are intermediate, right, between good conductors like metals and good insulators like ceramics or polymers.
Hence, semiconductor.
Exactly. But the truly revolutionary thing is that their electrical characteristics are incredibly sensitive to minute, precisely controlled concentrations of impurity atoms called dopants. We can control their conductivity over very small regions on a silicon chip.
Hmm.
This sensitivity is what made integrated circuitry, the microchip, possible. It totally changed electronics and computers over the past, 4 or 5 decades?
Unbelievable impact. What else falls under advanced materials?
Next, let's talk about biomaterials. These are non-living materials specifically designed and fabricated to be implanted into the human body. Their purpose is to replace diseased or injured parts. Think artificial joints, heart valves, dental implants, vascular grafts.
So materials interacting with living tissue.
Right, and the key challenge here is biocompatibility. The material must function reliably and safely while interacting intimately with living tissue. It can't cause harmful reactions like rejection or releasing toxic substances. It's a very complex and active field of research.
Makes sense. Then we have smart materials. These sound fascinating. Materials that can sense and react.
Yeah, they're really cool. Smart materials are able to sense changes in their surroundings, temperature, light, stress, magnetic field, whatever, and then respond to that stimulus in a predetermined, predictable, and usually reversible way. They almost mimic living organisms in that sense. A smart material or system usually has two main components: a sensor, which detects the input signal or stimulus,
Like a nerve ending?
sort of, yeah,
Hmm.
and an actuator, which then performs the responsive function, like a muscle.
What kind of responsive actions can these actuators perform?
They can do things like change shape, change their position, or even alter their mechanical characteristics like stiffness or viscosity
Based on the input?
based on the input. Common types of smart materials include shape memory alloys. These are metals that can be bent out of shape, but then when you heat them past a certain temperature, they snap back to their original remembered shape.
Kind of like magic wire.
Kind of. Then there are piezoelectric ceramics. If you apply an electric field, they expand or contract. Conversely, if you squeeze or bend them, they generate a small electric voltage.
Used in sensors and actuators.
Widely. Similarly, magnetostrictive materials change shape in response to a magnetic field, and then there are electroheological and magnetorheological fluids. These are liquids whose viscosity, their thickness or resistance to flow changes dramatically almost instantly when you apply an linearized electric or magnetic field.
Liquids that can turn almost solid.
Pretty much. Imagine shock absorbers that could stiffen up instantly when needed.
That's incredible. Are these used in real applications?
Oh yes. For example, the book mentions smart systems used in helicopters to reduce cockpit noise. Piezoelectric sensors embedded in the rotor blades monitor stresses and vibrations.
Yeah.
That data feeds into a computer, which then controls actuators, maybe other piezoelectrics, to generate precise anti-noise or vibrations that cancel out the noise from the rotors. It's active noise cancellation on a big scale.
Real-time adaptation using smart materials. Amazing. Okay, from the incredibly smart, let's go to the incredibly small. Nanomaterials. The chapter says they're distinguished not by their chemistry, but purely by their tiny size. How tiny are we talking again?
We're talking about materials that have structural features, particles, grains, layers on the order of a nanometer. So dimensions less than about 100 nanometers.
So small, we're almost manipulating individual atoms.
We're getting close to that level, yes. This involves what's often called the bottom-up approach to manufacturing. Instead of starting with a big piece and carving it down, top-down, we're designing and building structures almost atom by atom or molecule by molecule. Tools like scanning probe microscopes have enabled this.
And does being that small actually change the material's properties?
Dramatically. At this nanoscale, materials often exhibit unique and sometimes completely unexpected properties compared to their larger bulk counterparts. Opaque materials might become transparent. Solids might behave more like liquids. Chemically stable materials can become highly reactive or even combustible. Electrical insulators might start conducting electricity.
Why such drastic changes?
It's often due to two main factors. One is quantum mechanical effects, which become significant at these tiny dimensions. The other is the dramatically increased surface area to volume ratio. When particles are that small, a much larger fraction of their atoms are on the surface rather than buried inside, and surface atoms behave differently.
Makes sense. What are some applications for these tiny wonders, and are there any potential downsides?
Oh, applications are popping up everywhere. In catalytic converters for cars, making them more efficient. In new forms of carbon, like fullerenes, buckyballs, and carbon nanotubes, which have incredible strengths and electrical properties. They're used as reinforcement in automobile tires, improving wear resistance. In nanocomposites, mixing nanoparticles into polymers to boost properties. And in things like magnetic nanosized grains for hard disk drives, allowing much higher data storage densities.
So, lots of potential. What about downsides?
Well, precisely because of that extremely high surface area to volume ratio, nanomaterials can be highly chemically reactive. This has raised ongoing concerns about their environmental health and safety. There are questions about how readily they might be absorbed into the body, through skin, lungs, or the digestive tract, and whether they could pose health risks, like potential DNA damage or promoting certain cancers if exposure is high enough.
So, the safety aspect is still being actively researched.
Very much so. It's crucial to understand and manage any potential risks as these materials become more widespread.
This whole discussion about advanced materials, semiconductors, biomaterials, smart materials, nanomaterials really leads us directly to the big picture, the modern world's materials needs. What major challenges are material scientists and engineers tackling today that affect all of us?
Yeah, if we connect this back to the really big picture, material science and engineering is absolutely central to addressing some of humanity's most pressing global issues. First and foremost, energy. This is huge. It means developing new, more economical and renewable energy sources. Think more efficient solar cells, materials for wind turbines. It also means better energy storage batteries, especially things like lithium-ion batteries, with higher energy densities and longer life. And materials for more efficient hydrogen production and fuel cells, better catalysts. Materials are also absolutely critical for nuclear energy, everything from the fuel itself to containment structures and finding safe ways to dispose of nuclear waste.
So, energy generation, storage, efficiency, all heavily reliant on materials.
Absolutely. Second big area, the environment. This involves creating new materials specifically for pollution control, like better filters or catalysts to clean up emissions. It also means improving manufacturing processes to be less polluting and use less energy, reducing environmental degradation, and managing the whole life cycle, including the ecological impact of mining raw materials and disposing of products at the end of their life.
Sustainable materials and
Yeah,
processes.
exactly. And third, related to that is the issue of non-renewable resources. Many materials we rely on daily, like polymers derived from petroleum, or certain metals like copper or tin, come from finite sources that are gradually being depleted.
We're running out of some stuff.
We are, or at least the easily accessible sources. This forces us to do several things. Find new reserves, yes, but more importantly, develop innovative new materials that have comparable properties but are made from more abundant resources and have less environmental impact. And critically, we need to significantly increase recycling efforts and develop better recycling technologies. Considering the entire cradle-to-grave life cycle of a material is becoming absolutely essential.
Wow. So, material science isn't just about making cool new gadgets. It's fundamental to energy, the environment, and resource sustainability. As we wrap up this deep dive, I'm really struck by the breadth of what we've covered, from, the Stone Age tools right up to the nanoscale. It really puts into perspective how this core idea that processing dictates structure, which dictates properties and ultimately performance, is truly the invisible hand shaping our entire world. It's everywhere, even if we don't always see it.
Indeed. It's quite profound when you think about it. Consider the impact materials have had on past civilizations, shaping everything they did. And then think about the critical role materials play right now in developing solutions for our future clean energy, better healthcare, sustainable infrastructure, global connectivity. It's all tied to materials. And maybe the most exciting thought is, what groundbreaking material might be just around the corner? What discovery is waiting to happen that could solve our next really big challenge?
That is a truly thought-provoking idea to end on. what's next. Thank you so much for sharing all that insight today. It's been a fantastic journey through the fundamentals. And a warm thank you from the entire Last Minute Lecture team to all of you for tuning in and joining us on this deep dive.